Right, so let's have a look at this question. This is a question about a trolley and it's rolling down a slope and then it's stopping here. And it stops because of the friction for this part. And the idea of this type of question, anytime you see a height and some sort of movement, is it's conservation of energy question. And the general idea is we're going to be starting up with gravitational potential energy, which is just mgh, and that's going to turn into kinetic energy. And at the bottom of the slope here, we'll have the maximum kinetic energy, which is half mv squared. And then it will work against friction, and it'll have zero. Here it'll have zero kinetic energy because it's stopped, and also zero potential energy because it's relative to its starting position. Okay, so the interesting thing to work out is in this region, what you've actually got is work done against friction. And the work done against friction is equal to the frictional force times the distance it moves. And that triangle you really need to know. This triangle is work done at the top and then force and distance. It's a good one. So let's work out what they want us to do. They have plotted this d against h graph and they want the gradient. Now the gradient of a graph is equal to the change in the y-axis divided by the change in x-axis, which is just equal to d over h. So d over h is the gradient, and what they want us to do is to derive an expression for the gradient of the graph in terms of f, m, and g. So the thing that we're going to do is we're going to say that the initial setup, and when you use energy, you're always looking at the initial and the final, or the first and the second, and so on. So the initial energy is mgh, and this is going to be ending up being working against friction, and so we can say that that's going to be used up in doing the work against friction. So we're getting close. We can actually rearrange this any way we like. We can write it as mg equals fd over h by moving the h to the bottom, and we can also then do the next step as we can get rid of this f. And so we could write it as mg over f is equal to d over h. So these two steps mean that we can write it as an equivalence to the gradient. So the nice thing about that is then we can say that our gradient d over h is the same as, is equal to mg over f, which is an expression in terms of f, m, and g. And you don't really need to do more than that using conservation of energy. Right, that's the first part. The second part of the question is saying an identical trolley, so that's going to have the same mass, was placed at rest, so it's not moving at the bottom of the slope. And then when trolley A is released, it hits this one. So there's a collision. So you're thinking, collision is all going to be to do with momentum. And the idea is after the collision, the two trolleys joined together and moved off to the right. Okay, so the idea is the momentum conservation is before equals after. So let's work out what's the mass times the velocity before. Well, we've only got one thing moving. So you've got the mass of A times the velocity of A is equal to the, when they join together, mass of A plus the mass of B, because they're joined together now, times this new velocity v here, which is what we've got to find. Now, because they're identical, the mass of A is equal to the mass of B, so we can just say that if we're looking at this equation, it simplifies to MA times VA equals 2MA times V, what we're trying to find out. Now we can cancel the masses because they're the same, and we can say that what we're trying to find out, this one, V, just swapping it around so it's easier, V is equal to VA, the initial velocity of A, divided by 2. Right, so now we've got to find the initial velocity of A, and we can do that by using the conservation of energy, which will say that the mgh, the potential energy at the beginning, is going to turn into kinetic energy, half mv squared. So let's do this bit. mgh equals a half mv squared. It's the same m. And this velocity is the velocity of A. So to separate it, distinguish it from the velocity after they join, we're going to cancel the masses, rearrange this equation, and write, let's move that 2 up there. So we've got 2gh is equal to VA squared, or bringing it around the other way, VA is equal to the square root of 2gh. Right, so taking this now over here, we've got that the velocity is equal to root 2gh all over 2. That's what we've worked out. Now, the student has said that it's not quite the same as that. It's v equals root gh over 2. So is the student correct? Now we have to use a little bit of maths here to work this out, and we have to realize that 2 is equal to the square root of root 2, square root of 2, root 2, times root 2. That's the idea. So we can replace this 2 and write it as root 2gh, replacing this 2 as root 2 times root 2. And we can cancel one of these root 2's. Don't forget, we'll still have the root gh. Whoops. We'll still have root gh there. I lost that for a second. But we will, let's write it over here. So we'll have root gh on the top, divided by root 2. Now, we can say that that is the same as root gh over 2, which is what we were looking for. And that equals this velocity, equals v, equals root gh over 2. So the student is correct. It's probably important to say that. Student is correct. The new velocity is equal to root gh over 2. Right, question done.